So all of our cards are in the Padfolios that we had there. And then there's if you don't know who to reach out to, there's always the Rome at luc.edu or Vietnam at luc.edu that we are checking as well. So if it's like, oh, there's this course in Vietnam specifically, that's a good default to reach out to. But we're happy to, be first round of contact as well. Because in addition to recruiting for the
Okay, what about now? Okay, how about now? Julia, do you hear me? Okay. I'm so sorry about that, everyone. Please forgive me. Okay. I just will ask you for your Ignatian forgiveness. As you know, I talk a lot about that during my lectures. So, especially when I meet you on Fridays. So, anyway, I apologize for the sound problems. Let's try to start from the beginning then. So, I was basically recapping just a little bit about where we left off. So we were in the early electronic era of computing, and Dave and I were speaking to you about this very important question, which is how are computers really working? And especially those early computers that had like all those light bulbs or vacuum tubes, as we like to call them. What's really going on there? Okay, so this lecture is actually going to help you to understand some of that. And I have to fill in a lot of blanks here, though, so you'll be doing that as I go through this. So what I'm going to do is, so this is, if you're looking in the box folder, also there's this lecture, which is adapted from Bergen's notes, also on stored program computer editions. Okay. So, and then this is going to be the main subject of our lecture today, and it does take a little bit of time to go through because some of the concepts are a bit abstract, and then I'll try to explain them in more detail as we're talking here. So just to give you a little bit of a timeline here, okay, this is basically, some things that were happening with stored program computing. So this is like well after the time of the Atanasoff-Berry computer, which, as I mentioned, was 1936 time frame. Okay, and so that is considered by most people to be the first. Again, with the understanding that a lot of computers that preceded the Atanasoff-Berry computer, like especially the Hollerith machine, really are computers, but they are doing something a little bit different than what we're going to be describing here. So the first things first, there's the important thing to understand here is that basically there are two sort of parallel strands happening here, and I'm not going to read the slide to you because there's something I want to say that's different. The one strand is sort of the work happening on the ENIAC, and the one reason I had you watch that film is that the leader of the ENIAC project, there were two leaders, Eckert and Moschly, went to visit John Vincent Atanasoff in Iowa, and drew a great deal of inspiration from his particular computer design. And the reason I say this is because all of the mechanisms that made Berry's, the Atanasoff-Berry computer work also were present in the ENIAC. Right, now the other thing that's happening here in parallel, and Goldstein and von Neumann were both associated with this very famous project called the Manhattan Project. Okay, the Manhattan Project, I'm going to give you the Cliff Notes explanation of this now, and then what we'll probably do is maybe try to fill that in a little bit with even possibly a video. But Manhattan Project was one that brought together a lot of physicists to work on essentially what would become the atomic bomb. So, if you're, it was a secret project. And it was carried out mostly at places like, like Los Alamos National Laboratory today, but in New Mexico. So you even sometimes see the very famous videos of, bombs being detonated like in the desert. It was kind of like our version of what's happening in North Korea today, where there are all these underground detonations happening. So John von Neumann was, among many different hats he wore, he was one of the physicists who was involved in, developing ways of calculating, how bombs would work, how ballistics would work, and so on. Okay, so that's basically it. So the big thing is that he started working on actually a successor to the ENIAC computer, which was called the EDVAC. And the EDVAC is based on the principles that are just defined in this draft report that I'm going to talk about next. While I'm at it, let me try to make this a little bit bigger, okay, just so we can have a little more enjoyment. Okay, I'm trying to also get this thing out of my hair here. Okay. So online teaching is great, everyone, but like sometimes the technology can be really intrusive to the instructor, so I had to clear out a whole bunch of windows here. Okay, so anyway, so let's go ahead and take a look at this here. So John von Neumann, is often credited with having been the great inventor of computing as we know it. And I want to point out that the credit is deserved because there is a need in the world for people who we call great synthesizers who actually can take a number of ideas that are emerging and try to summarize them in a way that can be that can be used to drive future innovation. Okay, so let me just go ahead and tell you a little bit about this here. So basically, there were kind of two competing interests starting to happen around the time of this report. There are people who really wanted to, develop technology and especially computing technology for the good of scientific advancement, right? And I would put von Neumann in this category. And then there are people who wanted to monetize computing advancements. So, and actually people like Eckert and Moschly definitely would go on to form companies. And they were also engineers who were thinking about how they could, hopefully make money on their inventions. So, basically, von Neumann himself actually didn't necessarily write this report that's being discussed here, but he got a lot of input from the ENIAC team, which are the people who invented the ENIAC, and they contributed ideas to it. Okay, and then this fellow who had been involved in supporting the work, Goldstein, who actually was also part of this Manhattan Project, basically talks about the idea that the actual ideas of these letters were being bashed together to form this report. Okay, so it was kind of it's what we can call something that came together very rapidly, but actually now is extremely influential. So I want to talk a little bit about some things that are in this report. And actually, I have the PDF of this report, which I can share with you. I just haven't posted it yet. So anyway, so let's take a look at some of these definitions. And as I'm defining each of these terms, I'm going to go into some detail about them. So just to make sure we understand what we're seeing here, these are highlights from the report that was written by John von Neumann and the gang on the EDVAC. And they are considered to be the formative ideas of what really goes into a computer. And this is also related to the question that Dave was asking in last lecture is, what is a computer anyway? How are things really working? And this is something that in our book, we're going to try to do a really good job of explaining. So like the first thing is that when you're doing something with an electronic computer, the first thing we're talking about is what's called a high-speed computing system, because electronics, as I mentioned in the last lecture briefly, work at the speed of light. Okay. The second thing, okay, I'm sorry. So that's the very important thing to understand about what's called a digital computer or an electronic digital computer. Right? And then the next thing is this concept called logical control. So logical control means that you use like the same ideas you might have learned about in the Loyola Core when you took your philosophy course or your ethics course. One of the things you learn about is the importance of making logical arguments, right? So like if this is true, then then you can do something else. Okay, so that's basically where in the computer it's able to do the same kind of things that you could do if you had outlined the steps of a logical proof. Right, so those are the two things that are really endemic to the basic nature of a computer. Now then, the next thing is that the instructions. Okay, so I'm going to talk about that. So the instructions that govern a computer must be specified in exhaustive detail. So now what is an instruction? Well, if you remember when we were talking about Babbage's punch cards, that's a really good example of what an instruction is. An instruction is basically telling the computer to do something. You're either telling it to add numbers, you're telling it to determine whether something is true or false. You could be telling it to load a number. You could be telling it to store a number, and so on. And that's a key thing we're going to talk about in just a second. So just that concept of storage, I'm going to talk very specifically about, so I'll not say any more about it on this point. Okay, so they include all the information needed to solve a problem. This is very important. So when you write a program, you need to have everything in memory to solve it. I should point out that that's actually something that has changed today, is that because we have secondary storage, we don't need everything to be kept in memory all the time. But von Neumann's definition still applies because we need, at least while the program is running, to have everything it needs in memory. Okay, the third of the definitions is, once these instructions are given to the device, it must be able to carry them out completely without the need for further intelligent human intervention. So this is one of the really defining things of the beginning of the computing era, is that humans are not needed once they have actually written the program and loaded it onto the device. You might say, well, that sounds obvious. Well, think about it. If you put an app on your iPhone and then you needed to do something to fix the app while it was running, you would never use that app. Okay, so von Neumann's definition here is really something that has proven to be greatly influential of these three definitions, in fact. Because as we know, Babbage had already come up with the two previous ones, at least for his mechanical computer. But this idea of that, the computer can continuously run and do something with the program. And that's because it loads the data into memory. Babbage's computer could not do that. The program was still on the punch cards, and you'd have to replay the punch cards if you wanted to do anything. Now that assumed it worked, of course, which it didn't. But I'm just saying, at least you can keep that in mind. Okay, so now what are the actual components of a computer system? Okay, so, and this will probably not come as a surprise to you because I've kind of hammered home these ideas since we started the course. But the first is, since the device is a computer, it will have to perform the elementary operation of arithmetic. So in other words, you can't talk about something that's a computer unless it is like a calculator. It needs to be able to do everything that we would expect a good calculator to do. All right? And calculators, and do all of the operations of arithmetic, right? And they can also do them in the proper order. So that's the second point. The logical control of the device is the proper sequencing of its operations. So that is, when you write a program, based on the actual, inputs that the program receives, it will be able to decide what to do next. Okay, so that's what we mean by logical control. You can see here that in his report, he actually called it a control organ. There's kind of an interesting topic here that I feel like I should say something about, but I'll go ahead and skip it for now. But basically, the computer is almost a thinking type of machine. So we will come back to that when we speak about other people like Alan Turing. Okay, so I just want you to think, when you see words like organ, it almost suggests that it's like a part of the body, or body parts. Okay. So the third is that any device, and this is my favorite part here because it really brings it all together. Any device which is to carry out long and complicated sequences of operations must have a considerable memory. So this is really the part of the definition that makes a computer much different than what anybody definitely before von Neumann, Eckert, Moseley, and others had been thinking. Okay, so like when we get excited about all these devices like Babbage, we get excited about, we get excited about the Hollow Earth machine, we must understand these machines did not have an advanced memory concept. Today, you are all benefiting from this concept because you have so much RAM on your computer. The computer I'm using for today's lecture only has 16 gigabytes of RAM, right, which I consider to be very little. Those computers I showed you at Argonne have like 384 gig of RAM. And some other computers I'll be using soon have 1 terabyte of RAM. So RAM is the stuff that makes data-intensive computing possible. If you don't have RAM, it's very hard to do computations. So basically, then, in 1947, he's talking about like, this notion of how to, make machines that have more scalable memory. Okay, so and then this is with also John Moseley as an author. Now he's with a company by this time. That's the thing you want to notice here. So the computer that was built, to support this stored program, concept was called the EDVAC, Electronic Discrete Variable Automatic Computer. So when you have something that's like a discrete variable, it literally means that it takes up storage. Okay, so if you can just get past the big words here, the concept is very simple, even though it says electronic discrete variable automatic computer. Now you can see that by this time there are other people also starting to build machines. We have the Harvard Mark computers, the ENIAC itself, which was Moseley's computer, and then Bell Labs was starting to build computers as well. Okay, so I'll just keep going here. But the one thing is that there are 3 things by 1947 that Moseley is saying in this report that apply to all machines, right? So the 3 things that have impact on problem solving: the extensive internal memory, which we talked about, right? Elementary instructions. And see, so the thing is, the number of instructions you have are relatively few. That is, they're very focused on what things people need to do with a computer. So as I mentioned, arithmetic is one thing. Input and output's another thing. That would actually come a little bit later because, like storage was still catching up here. But, we definitely have like all those kinds of things. We have like, the ability to compare like 2 numbers for greater than, equal, less than. Okay, so that's more of interest probably to computer science students in the room, but it's definitely a salient point of computers. I'm actually a little surprised Bergen didn't put that in red because it's on equal importance with the other 2 points here. And then the ability to store instructions as well as quantities in memory. So what does that mean? That means that not only do the data you require to be in memory, but also the computer program itself must be in memory. Okay? And in fact, the key definition, not definition, but the key feature he points to is that we should also be able to modify the instructions that are stored in memory if we want to change the program. I'm going to actually take a brief detour here to tell you about my early experience with this concept. So back in the old days, All right, this is before, definitely before many of you were born, okay? Because, like I've been programming computers since the 1980s, okay? So that kind of gives you an idea of, like my relative age to yours. And the 1980s, when we wrote programs, we often would write programs that even could change themselves. So like you would have a program in memory, and let's say you had like a subtraction operation, you could actually have the program change the code to be an addition operation, all right, or whatever you wanted to do. You probably also know that there are these very famous viruses that basically find a way to get themselves installed on your computer. In the early days of DOS and Windows, viruses were really easy to create because the operating system didn't have what's called memory protection. So memory protection is a way of saying the way that the operating system says, you know what, you cannot touch this memory unless you have privileges to change it. Okay, so today, it's pretty difficult to write programs that do like what's described in number 3, but there's a long history before operating systems became very secure, where you could easily do what's called self-modifying code. Okay, so if you ever read up, this might be the kind of thing to use Wikipedia for because it's a cultural idea, but just read about self-modifying code sometime if you're interested in that. Okay, marching right along here. So, so again, what we're talking about here is the kind of influence on, on computing, especially modern computing. So this EDVAC, report, and the experience of EDVAC-like computers report by Mauchly, both of these, have led to a significant number of advances, that impacted modern computing in very profound ways. So once this report had come out, basically in 1947, there was this creation of this thing called delay line memory, right? And that's basically a way of actually, connecting connecting up a network of relays to store memory, okay? And then that memory can be brought to and from the central processing unit of the computer, for example. Okay. And then the ENIAC itself was updated to become a stored program computer. Now, if you remember those pictures I showed you, the computation was being done typically by just wiring up one component to another. But by 1947, they actually found a way to keep what are called function tables in memory, and those tables would do various calculations. So it was kind of like a hybrid computer, the von Neumann styles where you would put all of the instructions in memory, whereas the ENIAC computer was one that was designed to be wired up, but then they found a way to put that memory on the computer and make it work. So, and then of course by 1951, memory was a regular concept on the ENIAC. So again, you look at the time frame here, like from the time that von Neumann said, every machine should have memory, to the point where it actually started happening. It was a few years, but it did happen. By 1955, this computer was shut off, and I don't know the entire story of this actually, but basically, like many things, the actual units that were in production had been dumped off in a field somewhere, and this person actually found them and salvaged them. All right, so this is something kind of cool. And again, it's covered in our books as well. But one of the things that you want to understand is like just how getting to where we are today in computing is a result of what I like to call blood, sweat, and tears. And that is, you know, great sacrifices had to be made to build computers that could even do what you would think of today as being very simple. And you wouldn't even be impressed by some of these features today. But somebody had to spend toil for years to make it work. So all these inventors of computing, whether it's the ENIAC inventors, the EDVAC inventors, our man, Atanasov, they all had to, do what were called baby steps to make it possible even to do the simplest of computations. So first of all, the big thing, as I mentioned, is that this computer was a binary computer. So just like what Atanasov tried to do, it used base 2 as a number system. Okay, and then now so I'm going to be introducing some terms along the way here because we didn't cover all of them. But one of the things that because we have memory in computers, we need to break up the memory into manageable units. So this is for the non-computer science people in the room. A bit is a single digit of a binary number. Okay, so basically bits are 0 or 1. All right, and when you want to encode any kind of information, you have to be able to encode it in binary. Okay, so like you can see how if you only could do 0 or 1, that would not be useful for many things. But there is one thing that 0 and 1 can be used for, and it's kind of cool, and that is the notion of Boolean data. So like when you have true or false values, you can use binary. So 1 bit can actually be used to represent a Boolean value. Now, today's computers have so much memory that I don't think anybody really makes much of a distinction except for 0 and non-zero. So you can use any number of bits to represent a Boolean value, but 0 is conventionally the value we use for false. And then any non-zero number is considered to be true today. So you see here that the word size is 44 bits. So what this means is that you could represent any integer up to 2 to the 44th power minus 1. Now, it actually turns out to be 2 to the 43rd power minus 1 because most computers use what's called 1's complement to manage the word unit of the word unit of storage. So like 1 bit would be reserved for the sign, which is 0 or, minus 1 or 1. So that means you would use a 1 for something negative, and then you'd leave the bit empty as a 0 if you wanted to represent a positive number. All of that is related to the discussion I had earlier about Pascal's computer, which basically could only do forward arithmetic. So in microprocessors, including the EDVAC, you would actually do your math using that kind of method. So now instructions are the next thing. So the instructions on an EDVAC, there were only a very small number of them. In fact, there were 4 bits were used for what's called the operation code. So that means you can represent 2 to the 4th instructions, right? Now, and just so you know, the way that instructions work on computers is that they're divided between the opcode and the address. Okay, so the opcode is like the first 4 bits, and then 10 bits are used to represent the addresses on this machine. Addresses are which byte of memory are you addressing. So now look at this. So because it was a 10-bit address, that means that you can only manage 2 to the 10th number of bytes, right? So on the right side here, you will notice that the delay lines there could allowed you to access up to 1,024 words. Okay, by the way, I said the word bytes. I should have said the word word because that's what's used up here. So this is the basic storage size as a word, and then there are 1,024 of them. So this is actually a little bit more than 1,024 bytes because the word size here is about 8 times 5, 5.5 bytes today. One thing I need to point out is that in the early days of computing, people did not think about doing the memory in powers of 2, which you might find hard to believe, because they figured out that binary was useful. But today's, computers, basically almost always when you buy like something, you are working with like actual bytes that are 8 bits, and then that is usually some power of 2. So like whenever let's say you are going to the computer store, and you're like buying a hard drive, to put in your computer, you usually would buy something like a 256 gigabyte hard drive. You don't buy like 259 gigabytes, for example. Okay, and that has to do with the powers of 2 being now used uniformly in almost all aspects of computer design. So anyway, continuing along, so because we have these 4-bit instruct operation codes and 10-bit addresses, and the 10-bit addresses aren't important here, it's the 4 bits means that we have a total of 16 available instructions on the EDVAC computer. Now this may sound like not very many because today's computers, like if you have an Intel processor, hundreds of instructions. Okay, so there's like a lot more instructions on today's computers than in the days of the EDVAC. Okay, now again, you might say, well, no, that means the EDVAC wasn't very good. It's the opposite. They just didn't realize. You have to forgive them for not thinking that you would need to do anything with a computer other than arithmetic. Okay, so the big challenge was how to automate mathematical calculations. All right, well, I'm going to keep going for a little bit. So anyway, here are some, pictures that are showing what's going on here. These are actual drawings here. I believe these are von Neumann's drawings, actually. All right, you can see here though that it's a little hard to read all this, but here's the computers. Here's the control. What does that say? Magnetic tapes there? Yeah. Yeah, short memory, long memory. So here's another thing. There's something on this drawing, an oscilloscope. The oscilloscope was the only way to actually know what was happening in the computer. Okay, so an oscilloscope would show you like probably some signal, and then you'd be able to see whether, what the number was and so on from a calculation. And you can see there are wires going all over the place here. Okay, so that's like what the idea that, John von Neumann and the gang. I don't want to say just John von Neumann, but definitely this is like the first block diagram here of a real von Neumann computer. I think somebody just, okay, no, never mind. All right, so continuing along. So, these are just a few pictures here. I'm going to kind of skip some of that. So, again, I'm not going to necessarily go through all of these here, but I'll just say that, these are different. Let's just say this is part of a gathering story about computing. All right. So, and then we could, easily go into details at some point on each one of these, possibly by watching some films, though, because that's the best way to see about specific stories about some of these. But, so like you see here that, the Heath Robinson machine, this is used for basically, trying to do, again, primarily for doing, calculations. There was a lot of interest in Bletchley Park. As you probably know from my earlier discussions, this is a place where, they basically cracked the enigma okay, which was the machine Germany used to send encoded messages, in World War II. All right, Colossus is an actual computer that was also built around the same time, and this is, one that came out of the same place, Bletchley Park. Then we have the Whirlwind project. This is like for flight simulation at MIT. In fact, the Whirlwind is kind of an interesting project. I will try to show you something about this at some point. This project was one where it actually introduced something that was called a light pen, and that actually was the beginning of something that really was like a mouse. But it was also the beginning of something that was kind of like what we see in modern tablets, where you have a stylus. So you can see why you would need something like that if you were building a flight simulator, because you might want to actually be able to control, what is happening with the flight simulator. Okay, so this is the thing to understand here is that these dates are, this one here is the beginning of, of a flight simulator project at MIT. Okay, so these are all overlapping with the ENIAC invention of a working programmable computer. Okay, so basically this is where, like Turing, arrives in US. So he had already been, for a while. And then, he ended up being involved in also the code breaking effort, of the Enigma. So I'll try to show you a film on this at some point. There's a really nice one that I have used in the past. I'm going to see if I can get that. So just to say a little bit about the automatic computing engine, this is a machine that Turing wanted to build based on his abstract computing machine called the Turing machine, which was kind of like a Babbage-like computer where he had designed it in his head, and then he also wanted to build something for it. So he came up with this nice general purpose computer design. But I would say that he was largely a little bit late to the party. I mean, everybody, including von Neumann and Moschly, was already well on their way to figuring out how to make the engineering part of computing work. Okay. So the last few slides here are really about some work that these two guys who invented the ENIAC, did to form the electronic control company, and then like some of the inventions that were coming out of this. And so I usually skip most of this actually because I don't find it to be overly historical. However, there are a few things that I do want to say. So let's just take a look at each one of these. So this is like the Army, basically decided to fund these war school lectures to talk about advances that were happening in computing. And like a lot of these early figures in computing were invited to speak here. Okay. So the purpose of these lectures were to talk about different ways of storing things. Okay, so basically there are all these different types of devices for being able to store information and to be able to read the information back in. So you might be wondering, how does some of this stuff work actually? All right, so here's one that's kind of interesting. All right, so this is an example of like so this is an example of like an early hard disk here. Even though it says memory, it also is like a hard disk, because what you're doing is you're actually basically, to put something, to take something that's on the device and then remove it. And then of course, if an actual heat is detected, then it sends a signal saying that it saw a 1 or a 0 there. Okay, so this is an example of, it basically heats the surface with, of a drum cover with chalk, and then after it has done something with that storage unit, it then recycles the drum and refreshes all the spots. Okay, so this can be used for very short-term storage. Now again, you can see that these kind of things take It's just a drawing here, but this is something that would be taking up thousands of times more space than the memory on your computer today, which is all like solid state transistors. Um, so, but this shows you like how people, they have these kind of ingenious ideas. And even like a lot of the ideas of, modern spinning hard drives are based on the same concept of being able to like erase something that was like on recorded previously. All right. So here's another one, basically, there's a disk pin type memory system. This shares a lot in common with, without going into every aspect of how this works, the thing it shares a lot in common with what, Hollerith was trying to do with basically, having these pins where, like if the pin is sticking out, then it's storing a 1. If it's in, it's a 0. And then you could, of course, pass a current through it to determine whether there was a number there. There's this concept of delay lines, which is used to, this is one that might be even nice to show the video of. I put this video in here. Let me see if I can still get it. Give me just 1 second here.
Do this view.
I don't know if this can be heard or
This
not.
particular device was the first successful operating memory for a computer. It didn't hold a lot of information, but it allowed you to have enough information so that you could keep it off to the side, if you will, while you were doing other calculations. What is it? Well, there are 18 tanks, metal tanks here, aluminum. Within each tank was a long, narrow glass tube filled with mercury. How did it operate? Like sonar on a ship or a submarine. Electrical pulse would be generated to a sound pulse, would ripple down the liquid mercury in the tube, be detected on the other end, would be amplified and sent back to its origin. Point A to point B back to point A. The time it took to go from beginning to end and back to beginning, that delay was used and reformed into a type of memory that went into the calculations for the problem being solved at the moment. This particular item, UNIVAC memory, has a political history. This memory was part of the first computer to ever project the winner of an American presidential election, President Eisenhower in 1952. Of course, if the projections had been wrong, computing history might have been changed, but it was right, and it was 2 days before anybody else could verify what this projected.
So you can see that these are, like really big. The thing I was trying to get you to see there is that these are not like small time components here. So every one of these things that you see coming out of the Moore's lecture eventually found its way in some piece of hardware. That computer there was what the UNIVAC, which was created by the company that was started by Eckert. Okay, so there are a lot of these different ones here. Another very famous one is the Williams tube memory system here, right? So again, this one ended up in the EDVAC actually. Okay, and then we get to these rotating magnetic memories. These become very important influences on the hard drive design because, like I said, until you very recently, most computers were shipping with hard drives that had what's called spinning storage. Okay, so those are all traceable to this rotating drum type of design. They don't have no picture here, but I'm just telling you that that's like what the influence of that type of memory is. There are a few more I'm going to show you, and I think we'll go ahead and stop in a few minutes. But the thing that I want to show you is like the type of memory that would become very popular in the 1950s. Okay, so this is called magnetic core memory. And the way that core memory works is that it's arranged in basically a grid. Okay, and the way it works is that electrical currents are passing through here, and any location you want to magnetize, you just simply line up the electrical current on each of those dimensions, and then it will put it into a magnetic state, okay, that you can then read to find out what is the value of that memory. Okay, so each one of these is supposed to be encoding a bit of information. All right. One thing I want to say about that type of memory, I have a better picture here. So this is an actual a small scale version of what's called core memory. So this is something you might find hard to believe, but like in the 60s and 70s, this type of memory was used in computers. And then by the time we got to 1980, we had these smaller chips, okay, that encoded a lot more memory. So just take a look at the difference in scale here. Right, this is 16 by 64 bits. So that's 128 bytes of storage. All right, this card down, these chips down here, each one of these is a 16 kilobit chip. All right, you see that? So each one of those is 16 kilobits, and then there are 8 of them. So this is a 16 kilobyte memory card. Okay, so like this is the type of memory that was found in most of those early like TRS-80s, Commodore 64, which would come a little later, but the Commodore VIC-20 used this kind of memory, a variant of it. This is the kind that was found in much larger machines that were still, like filling up rooms. So this is what we're showing in this picture here are 2 different types of memory to come out of this core memory era. All right, so it's pretty awesome stuff. Okay, I'm seeing I'm out of time. So I'm gonna wrap up by saying that the rest of this is mostly about, like some of the technology. I'm gonna come back and say a few things about Whirlwind again next week. I'll probably even go ahead and say a little more about the British machines I was talking about. But I guess that's a good place to stop. So I hope everyone's having a good week so far, and we'll catch up next week. I mean, on Wednesday, I'm sorry, Wednesday. All right, well, thanks everyone. And I hope Dave will handle the export of the recording.